we speak about lift and project.
And Knapsack.
And Knapsack.
Yes.
Okay.
Something. Even I don't remember the exact title. But, okay. Anyway, thanks for the invitation and the suggestion to give a talk. Right. So the topic will be lift and project methods, or so just known as hierarchies. And the knapsack problem. Okay, now the knapsack problem is probably familiar to all of you. To me, it's become very familiar over the last day or so. It's the problem where the airline loses your luggage, and then you have a day to go into town with your knapsack and try to fill it up optimally with toiletries and groceries and things of this sort, so you can make it through the day. So you have, let's say, n possible items in the shop that you could possibly buy, and with each one you associate some weight and some kind of utility that it has for your reward. And so we have two sequences of n items. So you have the rewards, R1 through Rn, and the, say, weights, W1 through Wn. And let's just suppose all of these are integers. They don't have to be. And then you have some kind of capacity, which is how much you can carry after, spending a whole day in transit. So you have some capacity W. And what you would like to do is basically find an optimal set of items. So you want to find some optimal set S such that the total weight of the set should be at most your capacity, and you want to maximize the total reward that you get from the same set, right? So here it would be summation over the same set and total reward. Okay, so this is a classical optimization, integer optimization problem, and in the approximation world, and at least from the computer science perspective, this is a hard problem to solve. So rather than try to solve it optimally for specific instances, what we would like to do is find some solution which is a feasible solution, but is not necessarily optimal. It's not doesn't necessarily maximize the total reward, but maybe gets as close to it as possible. And what we in fact know is that you can find a set which is close to opt within any, almost any factor. So if you want a 1 minus epsilon factor, even if epsilon is 1 over some polynomial in n, this can still be done in time, which is polynomial in n, say. Right, so when I give this talk in a more computer science setting, then it's very strange that I start to talk about sort of, new approaches for Knapsack, because this is sort of an infamously easy problem from a computational point of view, right? I mean, it's as easy to approximate as anything which can't be computed exactly. So then, that raises the question of, why throw all this heavy optimization machinery at it? And the reason is that...
Polynomial is easy. The Knapsack is not easy.
No, it's
Is it easy to approximate?
It's easy to approximate.
Does it have an FP+?
Exactly, yeah. So within the various broad categories of problems which are hard to compute exactly, this is in some sense in the easiest category. Right. So then what I like to say is that if we look at the sort of optimization tools that we use today for approximation algorithms, it's important not just to sort of go problem by problem and understand, how easy it is to compute or to approximate, but also to understand the tools themselves. And I think this particular problem, the knapsack problem, is really nice because it really, some of the tools that I'm going to talk about, it really illustrates very beautifully and simply the power that each of them has, and sort of draws a nice contrast between these different tools. And specifically what I have in mind is this lift and project approach, which I'm going to talk about. But first, let's just review sort of what the classical approach is. So we have this combinatorial optimization problem. First thing we do is write some LP relaxation for it, right? So rather than this, we write it as, okay. So I'm going to call this opt throughout, and we'll define opt LP to be the maximum possible reward. And now this summation is always going to be from 1 to n for any solution xi which satisfies this constraint, right? So this is written as xi wi. The summation is at most w, and this is now a continuous problem, not an integer problem. So these are going to be variables between 0 and 1. And this we know how to solve, and then the question is, how does this optimum relate to the actual optimum? And in fact, it relates quite poorly. But one nice property we have, which I don't know if I'll prove, but maybe I'll talk about very briefly, is the following lemma. So if we have any LP solution, xi, which is the feasible solution of reward r, there exists some integer solution of reward which is at least the same reward, and we lose something which is, so now if we think of this solution as possibly a mixed integer solution, so some of the x's are 0, 1, and some of them have fractional value, what we're going to lose is the worst reward we have for the fractional xi's. Okay, so if we look just at the i's for which xi is not 0 or 1, we lose the maximum reward we have for such xi's. And the reason for this is that we actually understand very well the structure of the optimum solution for this LP, or even for a mixed integer LP. And it is, if we take a general solution, or a solution where we already establish the xi's, some of the xi's to be 0 or 1, the remaining fractional values, the best way to choose them fractionally is just to pack them greedily. So we sort them by their density, or by how much reward we get per weight, and then we just, we pack them into the remaining capacity, and then the last one is the one that we can throw away. And so we don't know, right, because we didn't sort them by reward, we sorted them by reward divided by weight, but then, so we don't know exactly what its reward is going to be, but in the worst case it will be the maximum reward for the xi's which we didn't already choose to be 0 or 1. So I don't want to dwell on this too much, but this is a very well-known sort of result. And so this is very nice, and in fact, if all the rewards are very small relative to the optimum solution, or maybe all the rewards that haven't yet, for variables that we haven't yet chosen to be 0 or 1 are very small, this in fact gives us a great approximation, right? This gives us some integer solution which is very close to the fractional optimum, and then the fractional optimum is at least the integer optimum, so it all works out very nicely. By the way, I should say before I go any further that this is an audience with sort of very diverse background, so if at any point I start to throw around terms that are not familiar, then you can feel free to also start throwing things at me as well to stop me and let me know that I should define things and explain and so on. Okay, right. So this lemma is great. This really solves the problem up to some very nice approximation factor if these rewards are very small. But if the rewards are huge, then obviously we're going to be in trouble. And as a very simple example, if you just think of a knapsack instance of size 2, where you have one item, which is also the size of the capacity, which has unit capacity, and then you have one item which also has, which doesn't fit in the knapsack, so it has size 2, but it has some huge reward, then obviously the LP really wants to take this item, this second item, even though it doesn't fit. And what the LP will do is just take this fractionally with weight xi equal to half, and it will get this wonderful reward. But in reality, in the integer world, the only thing we can do is just take the first item. So in terms of approximability, there's a huge integrality gap here. There's a huge gap between in the worst case, between the optimum fractional solution and the optimum integer solution. And what we would like to do to deal with this is start to massage this LP relaxation. Where is it? Here. Start to massage this LP relaxation so that we can get this bound down to something more reasonable. And in some sense, we would expect this to happen, because we know from the combinatorial optimization world, from combinatorial algorithms that don't have any kind of continuous optimization going on, that in fact this is a very easy problem to approximate. So it really doesn't make sense that these very powerful tools wouldn't capture some of the very simple algorithms we have to approximate this problem. So one thing we can do okay, so this is my bad example. And one thing we can do is obviously to start to add more constraints to better describe the integer program. And we can add constraints such as, so let's see. So let's call our next relaxation LP star. So opt LP star is going to be, again, the maximum value, right? Still has to be feasible. Still all the xi's are between 0 and 1. And now we add one more constraint, which is that, okay, I just erased it, but what was the problem with the instance that I had before? It was that, the LP was trying to grab some item which was very clearly, completely inappropriate. So if, let's say for all such items, for all I such that, we can't even take this item on its own to be in the knapsack, we're just going to set the corresponding xi to 0. So this is a much more reasonable relaxation because it prevents you from trying to even fractionally grab any item which wouldn't even fit on its own. And in fact, already this relaxation gets us down to a integrality gap of 2. And the reason is that, so maybe this is just a second to explain. Okay, and the optimum of this new LP is at most, where am I? Is at most 2 times the actual optimum. And the proof is very simple. We just use the lemma, right? So if we look at the, okay, so if we take the optimum, okay, so we have some, let's move things around here. Okay, we know that there is some solution which has a reward, at least whatever reward we already had, so it's the optimum of this LP minus the maximum Ri, where xi is not 0 or 1. So if we just move things around here, then we get, right, so we have optimum. Fractional optimum is at most opt plus this. And note that now that we threw out all the xi's corresponding to items that don't fit on their own, every such Ri is a reward which is at most the optimum. Because every xi which is fractional necessarily is not one of these i's. It's an I such that we could take just that item on its own to be in the knapsack. So it's a feasible solution just on its own. Okay, so this in itself is at most the actual optimum. So in total we get twice the optimum. So this has an integrality gap of at most 2. Okay, let's see. Okay. So now, but still 2 is very bad for a problem which is essentially as easy to approximate as anything which can't be computed exactly in polynomial time. We really expect to have some kind of relaxation which captures which captures the approximation algorithms we already have and gets us down from 2 to 1 plus epsilon for any epsilon. And what I'd like to do, or what I like to do in general, is to move away from this sort of somewhat ad hoc approach, which says, okay, let's look at the problem and let's, let's see if we can tweak or strengthen our relaxation in some way which helps us in the analysis for this specific problem. Instead of that, what I like to do is look at the sort of tools we already have. And specifically, I have in mind this lift and project approach. So we already have these systematic tools for strengthening relaxations, and often. And what's nice to do is sort of to take this machinery and develop machinery for understanding how these lift and project methods give us newer relaxations in some kind of, way that we can, in a way that we can sort of transfer from problem to problem rather than having to sort of hammer away at every combinatorial optimization problem on its own. Okay, so our goal is going to be to find the relaxation with an integrality gap which is most 1 plus epsilon for any epsilon greater than 0. In fact, what would really be great is if we could do this for epsilon which is polynomially small. At this point, we still don't know how to do that, but at least we can capture the fact that, for any constant approximation factor, we have some kind of convex relaxation which captures a certain kind of algorithm with that approximation factor. Okay, so okay, maybe I should use this part now.
The goal is not just to find this abstractly, but to construct this in polynomial time, this relaxation?
Yeah, so yes, in fact we're going to use sort of these ready-made hierarchies which give us the exact way in which we formulate such a relaxation, and the goal is to really understand the connection between these relaxations that we get from these hierarchies and the actual optimum when we apply them to the knapsack problem. Let's see. How do I get access to this board now? Okay. I'm not sure if that's what was supposed to happen. Okay, so let's try that. Okay. All right. So this was the first part of the title, the knapsack problem. Now I want to talk about lift and project methods, or LP hierarchies. Well, hierarchies in general, not just for convex optimization problems. Okay, so now okay, so what's the idea behind these hierarchies? The idea is you take some combinatorial optimization problem, you think of it as some integer optimization problem or some polynomial optimization problem, and then instead of just saying, okay, we're going to write one relaxation, one linear program relaxation or one semi-definite programming relaxation or what have you, we're going to sort of take the original formulation of this problem and build a whole sequence of relaxations. And obviously we're going to pay something when we build this sequence. The sequence is going to construct relaxations whose description gets larger and larger and very quickly becomes unmanageable. But we're interested really in the first constant many levels where we can still do optimization in time which is polynomial in the original description of the problem. Okay. And this is really caught on in the last few years in the approximation algorithms world, because we've found that, this is sort of a toy example, this knapsack problem for us, because we already understand knapsack very well, and it's maybe not even interesting for a lot of people in computer science. But for other problems where we've been stuck for years, or maybe newer problems that we didn't know how to deal with, this approach has actually given us state-of-the-art approximations and tools that we never had before. So this has become extremely useful, and one thing I'd like to do is sort of understand the tools themselves from the approximation point of view. Not from the point of view of, what problems does it capture exactly, but from the point of view of what kind of approximation algorithms does it capture. So in general, the idea is that instead of looking just at a relaxation for the original variables, so the simple relaxation or the simple LP relaxation is for is for this problem, right? It's for the convex hull of the original problem, right? And all the zi's on 0, 1, or just write the vector z is 0, 1 to the n, and it's a feasible integer solution, right? And so these, for Knapsack and for other problems in general, this is typically what we have. We have some, what we really would like to solve is this problem. We'd like to find a point which is in the convex hull of integer solutions, but we actually find some arbitrary fractional solution which just satisfies some basic properties that points in this set would satisfy. So instead of this, what we'd like to do is sort of extend this to look at more variables. Obviously, we don't just have arbitrary variables, but something that's a function of this. So what we do is we write a relaxation not for this, but for moment vectors. Okay, so now instead of having something in the in the convex hull of these points, we have something in the convex hull of, so I'm going to write this as Zi. So now these are indexed by subsets of 1 through n. And at a specific level of a hierarchy, we're only going to allow these subsets to be so large. Okay, so all these are going to be bounded by some, in our case, some integer k, which is fixed and not dependent on n. Okay, and then the requirement is going to be the same, that this is right. All the vertices of the polytope will be feasible. Okay, and just note. Let's give this some name. So let's call this I don't know.
So your moment vectors of weight at most k are just feasible integer solutions.
Right, those are the vertices of the polytope, and then we're going to look at the convex hull.
So the variable z subscript I represents the product of the original z variables in the
Yes,
I.
so I forgot to say that. Yes. I is a product of z subscript I, and we're going to identify the singleton z's with the zi's here. Yes, it's clearly missing from my notes. Okay, thanks. Right, yeah, so this, we're not adding arbitrary variables, we're adding variables which are functions of the original variables. And then the empty product, just think of it as one. Good. Any other questions? Omissions? Okay. Right, so this is still the same problem, but somehow the fact that we have these extra variables gives us some power to play around with them and introduce some very powerful constraints. And just note that if y yi, okay, let's call this 1. Is some point in the convex hull of these solutions, so y is indexed just like these z's, then if we define, let's take y, say tilde, to be just the sets which are at most k over 2, or size at most k over 2, okay, then this matrix, which I'm going to call the moment matrix, which we define as such. It's going to be indexed by these sets of size at most k over 2. And in the ij position, we're going to have, sorry, this is m of, or yeah, actually we don't need this. Oh yeah, we do need. All right. Then this this matrix, which is indexed by the sets, right? This is most k over 2, and right, it's defined like so. This is in fact for y's. Okay, how do I say this? So this is a bit tricky, but if y okay, if this y is represented as some convex combination of these zi's. Let's write it. Okay, so these are the z's which represent this y. Then this matrix is actually summation over, this would be z transpose, and times alpha s. Okay, this is certainly true for 0-1 solutions, right? Because it's the z indexed by the product by the union is just the product of the two z's for 0-1. And then, and this is obviously, each one of these is positive semi-definite, each one of these products. And sort of by definition, because if you multiply by one vector on the left and one vector on the right, you're going to get something non-negative. So this is PSD, and then obviously the convex combination of these is also going to be PSD. So, I don't know if I should.
Excuse me?
Yes.
So this equality holds even if, so it's clear that it holds if y is the linear combination of these sets.
Yeah.
But it also holds if you take just this restriction to half degree with y tilde.
Yeah.
Oh, and if you go even below, it might not hold. Even if I have just that up to degree 1
Yeah.
y coincides with linear combination of the sets.
Yeah, that's any submatrix, which is indexed by i's which go up to anything which is even less than k over 2 is also fine.
Okay.
Yeah.
Yeah, because it's a minor, right?
Yeah.
Also this
Of the matrix.
y.
Yeah.
Well,
So
I just thought of
so
this
the
equality were equality the last equation sign here before that, yes, here.
Yeah.
In between these, yes.
Yeah.
Is it,
Yeah, so if this is indexed by i's which are at most anything less than k over 2.
yeah,
it's-
but the entries go up to degree k somehow, right? So the I union j could be an arbitrary set of degree k.
That's why it's a relaxation, right? Otherwise it would be integrals.
Yeah. Okay, maybe you can discuss this later.
Okay. Maybe I misunderstood the question.
So is it also true if you know just that y1 is 1 and y of an empty set is 1 and y of a singleton set corresponds to the components of this linear combination of the sets?
So all the y singletons are 1?
So, sorry?
I mean, you should think of the rows and columns indexed by subsets, so you can order them, you know, in your favorite order. So then your linear part would become a minor, like upper left corner of this matrix.
Yes.
So it will be PPSD as well. So what's the question?
Well, the question was not about the fact being PSD, but about the fact that this matrix is actually a linear combination of these rank 1 matrices.
Kind of y I union j is equal to yi times yj.
No, that's not true. I mean, y is are moments of a measure somehow, right? So it's not
Well,
multiplicative.
the extreme point, you get rid of the convex bit. Because it's not without the convex bit, without the convex bit, you get some nice one.
Okay, maybe let's discuss after. I just didn't understand why you go to this half degree, why you need this y tilde.
Oh,
Why
why
you
I don't
need
go
this
all the way
code?
up to k? Or what's,
Well, because
would you like it to be larger or smaller?
both is okay for me, but if it goes up to k, then everything is clear to me.
If
If it goes up
k,
to
then
1,
these
it
are
might
not-
still be okay. I
If
don't
it
know.
goes up to k, then these are not defined yet. Oh, you're
Well,
saying you're
no, but-
only going to...
No, but when you have a y in the line above, you have y equals yi, right?
Left, go left.
So this goes up to k. So you have note y is a family indexed by i's which go up to k, which are subsets of degree at most k.
Yeah,
But in the next line, you define the restriction of y
Yeah, because-
subsets of.
because here in the matrix we're going to have yi union j, so
Yes.
it's not going to be defined if I and j are, say, disjoint, and each of them is of size k.
Of course, so I understand the first line, but I don't understand why you need the y tilde. That's what I don't understand.
Oh, yeah, I could just define. Yeah, I mean it doesn't. Oh, I see. Because these z's are not restricted or something. Okay,
Should be
so
y,
I'm,
without the tilde.
yeah, okay.
No y tilde is only once.
You didn't write to it.
Yeah, it's okay.
Okay.
I was trying to get to these z's which are, yeah, but it's not in, okay, it's fine. Okay. No, it's not. It's not fine, right? Because you want these z's. This product is. It's not going to have the right dimension, right? No, it should be y2. Yeah, these z's need to be the right dimension to give this matrix. Otherwise,
Okay.
yeah. Okay, good.
Sorry.
Yeah, no, it's okay. Clarified that, good. All right, so what did I want to say? Right, so, but this is all, this is all sort of a Knapsack experiment. I like to throw out that word, especially in Israel. Right, so this is something we don't really know how to optimize over efficiently. We probably can't do it. So we write some relaxation for this. But the relaxation is going to have sort of the same indices, and it's going to try to capture some of the same properties. And there are a number of, so this is the general idea, this is what we're trying to write relaxations for when we talk about hierarchies. And there are a number of different approaches. There's a hierarchy due to Shiralian atoms, there's one due to Lomas and Stiver, there's a more recent one due to Lassell, and there's some others, and they're all trying to sort of capture this same idea in different ways and use sort of different subsets of the properties of this moment vector in ways that are still sort of solvable in polynomial time. And there's sort of two different approaches we can have in approximation algorithms in sort of deciding which tool we want to use. One thing we can do is say, okay, let's just use the most powerful tool, the one which gives the strongest relaxation, and it's going to have all the properties that all the other tools will have, and that's the best hammer we can throw at our problem, and it will give us the best approximation, and then we're happy. But a different approach might be to say, rather than take your heaviest hammer, use actually of these various hierarchies, use the tool which only captures the minimum characteristics or the minimum properties that we need for our algorithm to work. So there are two reasons why we would actually not want to use the most powerful tool at our disposal. One reason is that it might be faster to solve, right? It might be, you have fewer properties, it might be easier to optimize over in practice, also in theory. And another reason is that we really want to understand what these tools are doing. We don't want to just throw everything we can at the problem and then not really understand where the improvement came from. We want to know exactly what it is that's allowing us to get some good approximation and really understand it well. And in that case, we can even sometimes sort of close the problem from both directions, because if the tool is very simple, we can also construct lower bounds which match or nearly match the performance we're getting from the specific tool that we choose, and then we really understand what we're dealing with. And for some of these more powerful hierarchies, like the Lasserre hierarchy, people have been working extremely hard to get bad integrality gap examples, and one of the reasons is that it just has such powerful properties that it's very difficult to construct examples where where they're not already capturing exactly what we wanted to do. Where you can really cheat by choosing some fractional solution which is very far in terms of the objective function. Okay, so the one that I'd like to focus on today is actually one of the earliest ones. It's the Lovász-Stuyver hierarchy. And it's been looked at a lot from the side of constructing bad examples, constructing for various problems large integrality gaps, and less from the positive point of view, because it is fairly weak compared to some of the other hierarchies, and it has such a simple structure that it's relatively very easy to construct bad examples for. But for this, it really is all we need, up to the caveat that we need semi-definite programming. It won't work with linear programming. In fact, it seems like linear programming won't help us in general. But we'll get to that in a second. So the idea in LS is that we want to get at this convex combination. We want to sort of get at this convex combination of integer solutions, and we do it in this case by sort of looking at one index one singleton at a time. So each time we're going to sort of choose one of our little i's and try to see if we can separate the solutions into, or separate this convex combination into the solutions which set it to 0 and the solutions which set it to 1, and sort of go variable by variable. Okay, so what's the idea? All right, so if we have x, right, and now this is okay, so this is the integer world, and now this is going to be the relaxation world, right? So this x is a relaxation at level k of the hierarchy, if and only if there exists some y Now y is going to be just a second moment vector. It's only going to have, y empty set, y singletons, and y indexed by I and j, such that some of the properties that you would expect to hold really hold. And right, so one thing is it should tell us how to separate for every index, how to separate x into a solution which sets xi to 0 and a solution which sets xi to 1 in the natural way according to the moment vector. Okay, so there exists, and the way this hierarchy works is recursively. The solutions which set such that, for all I from 1 to n, there exist such solutions, and it's going to work recursively. We're going to be able to pick any index and sort of find these two solutions at one level below, and the first level is, let's say, just the first LP we started from, such that so x is going to be a convex combination of these in the natural way, which follows from yi, or follows from just the value of xi, right? So it'll be xi x1 plus 1 minus I x0. Okay. It has to be, and in addition, we can use the information we get from the moment vector to tell us what these xi's should be. So if we look at the vector which in the j position has y ij, this will be xi times x1. And if we look at the vector which is indexed by, need a little more space here, here we'll have y j minus yij. This is the, up to the right factor, the vector x0. And this is just decomposing x into a solution which sets xi to 1, a solution which sets xi to 0, in completely the natural way if yi was really a second moment vector. So it's sort of, it's a lot of math, but it really is, exactly what you would get if you knew the second moments, and and you wanted to know how to set xi to 1 or 0 in this decomposition, which disappeared here. Okay. Okay.
What is the PSD is?
Right. Okay. So this is the LS hierarchy. This is Lova-Schreiber without SDPs, and so this is right. This is LS, and then there's the SDP version. Which is all of this, and also requires that the moment matrix that I defined here, but now it's not defined like this. It's just defined by these yi union j's, and now this is going to be a singleton or the empty set. That this is also PSD, and we know that if it really was a moment vector of something in the integer polytope, then it really would be PSD. Okay. So
Excuse me?
yes.
May I come back to a question before?
Yes.
So I thought about it. So in this, what is written above Lova-Schreiber now?
Uh-huh.
So you are claiming that, this cannot be true. If you're claiming that if you have a measure, so this is this linear combination of the Dirac measures in these sets, right? And if you have some other moment sequence which comes from a measure, and if the moments are the same up to degree k half, then they would be the same up to degree k, right? Because this y tilde equals the sum of the alpha s z s. This says that the moments up to degree k half coincide. And then in the line above, you are saying that the moments up to degree k coincide, right? And maybe I'm getting something completely wrong, but because this equality of
let's
two
forget
matrices.
for a second about the convex combination and just think of an integer solution.
Well, of course, yeah.
Yeah.
I mean, a convex
So-
combination of integer solutions, right?
Yeah.
So
if you just multiply this z by z transpose, where the z's are indexed only up to sets of size k over 2,
yes,
then in this position we're going to have zi times zj.
but the equality of these two matrices says that all moments, or the yi's are the moments of the Dirac measures of a linear combination of Diracs in the sets.
Let's just think of y is equal to z. I mean, it should be clear that it's okay after we convexify.
So using it, it's over 0 and 1.
Yes, yes.
Yeah, maybe that's.
So this is really used here.
Yeah, yeah.
Okay. So I have to think about why this is true. Okay. So when that was my problem, because I was
it's
thinking
just
of
if you-
arbitrary measures.
No. You just think of. I mean, first of all, it's I mean, it only has a finite number of points, but if you think of the z's which are all 0, 1, right? Then zi times zj is just like this product. Zi times zj and
Basically,
Right,
have
this-
zi squared is all equal to zi.
yeah. So alternatively, it's always 1 unless one of these is 0.
Yeah, that's okay. But if for k equal 1, it's definitely not true. Or for k equal, let's say, for k equals 0, it would definitely not be true. For k equals 1. Sorry, for k equals
Well, we're assuming that we have the z's for all the. We're assuming that z is defined for all sets up to size k.
Yeah, I find it helpful to think of the z as being, you're taking all the moments up to a certain degree and you're just putting in a long vector,
Yeah.
and then you're going to take whatever it is out product, without any transpose, and then you're going to get this bigger matrix that contains the powers that are twice as high. That's what you're doing, isn't it?
That's right.
But you're saying if the moments if you have 0, 1 random variables, right? And if the moments up to degree k half coincide, then the moments up to degree k coincide. I mean, this is somehow.
No, we're assuming that the.
This is very strange because the equality of these two matrices of a matrix M of y and of a linear combination of these Z transpose.
But I'm assuming that the moments coincide for everything up to size k.
Okay. Yeah, just hold them, it's all right.
I'm not assuming that.
Okay.
I'm not
I think
assuming.
I have to discuss with you afterwards.
Okay,
Sorry.
I'm not assuming that it's only up to size k. I'm just for the purpose of defining this product, it's up to size k over 2. But
No,
in
no,
terms
that's
of,
okay.
okay.
That's okay. That's okay.
I see. All right. Okay, so let's see. All right, so that's ls. That's ls plus. Right, we have all this. This good. Right, and so what I'd like to claim, maybe in the interest of time, I won't even prove it, but I'd like to claim that just applying one level, even of the LP, already gets us, it's as powerful, at least as powerful as this LP star that, where is it? Oh, here, yeah, where we said, we're not going to allow any items to have positive value if the item doesn't fit on its own in the knapsack. And the reason is that here, when we do this kind of conditioning step, even if we just do it once, then any xi which has positive value has some corresponding x1 solution where xi actually equals 1, and it's still a feasible solution. So in that case, there's no way xi could be, or I could be one of the items where, you know, just that item on its own doesn't fit, because you're going to have some solution where you have that item and possibly some fractional value associated with other items, and it's definitely not going to be feasible, right? So it has to be a convex combination of solutions where this xi is always set to 0. And in particular, it's also going to be set to 0. Okay, so even just one level of LS gives us this sort of power where, you know, we go from an unbounded integrality gap to an integrality gap of 2, and then you would hope that, you know, maybe if you do one more round of LS, then it will go down to 1.5 or something else, and you just keep going up, just the linear programming hierarchy, and get this goal of, you know, going down to 1 plus epsilon. And in fact, it doesn't happen. But before I tell you why it doesn't happen, I'll tell you why at first you would think it should happen. What we want to do is, I guess that's good, right? So what we would like to do is imitate a kind of combinatorial approximation algorithm, which gives us this 1 plus epsilon approximation without any, without any actual optimization, no convex optimization involved. So we'd like to imitate this combinatorial algorithm. And what does this algorithm do? Well, first, this might be up to a constant times epsilon. So first we sort of guess some set S epsilon, which is all the indices corresponding to items which have reward, which is relatively large. It's at least epsilon times the optimum. Now, in reality, we don't know what opt is, but this is just some threshold set. It's all items above a certain weight. So if a reward, so if we just, we can guess it by just trying, n times, you sort it by reward and then try every possible suffix of this set. So we can effectively guess this. One of the guesses will be correct. And then note that for any feasible set, which is a solution to the original problem, we have its intersection, or the number of items it has in this set, is at most 1 over epsilon. And the reason is that every such item corresponds at least epsilon times the optimum value or optimum reward. And if we had more than 1 over epsilon such items in some solution, then the total reward they would give is at least is more than the optimum, right? And so the solution couldn't possibly be feasible because the best solution only has reward opt. You couldn't have a solution with reward greater than opt. Okay. So then we can actually also guess so then we can also guess, once we've guessed S epsilon, we can also guess S intersection S epsilon because this only has a constant size, right? So there are only n to the 1 over epsilon possibilities. And one of these guesses will also be correct. Okay, so once we know S and we know we know S epsilon and we know which items from S epsilon are in the solution, the only thing that remains is to find or try to approximate what the best remaining items are that we need to choose. And all these items are not going to be in this set. They're going to have small reward. Right? So there we can also write an LP and we can sort of round it in the obvious way, and then what we lose is only going to be very small. It's only going to be this epsilon times opt. Okay, so then we only need to write LP and round for small reward items. And by dilemma, we only lose epsilon, at most epsilon times the optimum. Okay. So why would we think that hierarchies should help us? Let's get back to that. Okay, so we would think that hierarchies should help because, in essence, what we would do is, we don't have to guess this opt because we can substitute for it the optimum of the relaxation, and the analysis still goes through. And we also don't have to guess this intersection because what we can do, what LS allows us to do, is sort of pick any item which still has positive value, even if it's fractional, and say, okay, if the value is not 0, then there exists some solution where xi equals 1. So we can sort of do this conditioning step and we'll get some solution where that equals 1, and after it equals 1, because it's a convex combination, that 1 never goes away. It always remains 1. So we can go through. All right. So here's the hierarchy version of that. So the first step. Right, so S epsilon is now just going to be Ri, whose reward is at least epsilon times the optimum of, let's say, the kth LP, where now, let's say, k is going to be order 1 over epsilon. In this hierarchy, and as long as there exists any I in S epsilon with fractional value, so xi is not 0 or 1, we sort of condition on xi being equal to 1 in this way by sort of choosing that index and looking at the corresponding moment matrix and extracting the solution where xi equals 1. And just note that we're not and note that we can't have more than 1 over epsilon items, because then 1 over epsilon items would give us a set with reward which is more than 1 over epsilon items would give us a set with reward which is more than this LP optimum, and the LP optimum is more than the combinatorial optimum, and that's going to be a contradiction. Okay, so again, and this can happen at most 1 over epsilon times. And after we did this conditioning 1 over epsilon times, then we're only left with items which have very small reward relative to this LP optimum, and we're only going to lose epsilon times the LP optimum, and then we're happy. And there's a reason why I didn't write this on the board, because it's absolutely not true. But it sounds very logical. I mean, you do this conditioning step 1 over epsilon times. You sort of you force this set, or you force the solution on this set to be integer, and then you round the remaining ones, and the remaining ones have very small reward relative to your fractional opt, and that's all you're going to lose. Okay. So where did I cheat? So first of all, was this lie clear, at least? I'm claiming that there's only a constant number of times you can do this conditioning, so you only need a constant number of rounds in this hierarchy. And then after you do this conditioning, this part of the LP becomes integer, and then you round the remaining part. The remaining part is only small reward items. Small reward items only lose epsilon relative to the LP value. Okay. So I'm not sure if the lie itself wasn't clear, or if it's clear why it's not clear why it's a lie. Okay. I'm going to be optimistic and hope that it's the second. Okay. The lie is that when we chose this set of items with large reward, and its complement is the items that have small reward, the question is small reward relative to what? It's small reward relative to the original LP value. But after we do this conditioning, we're not rounding the original LP. We're rounding some new LP solution, which we arrived at after doing a number of these conditioning steps. And this solution could be much smaller than the original. So when I say we're losing something, so this analysis is for something that's in some sense unrelated to the original LP. Right, it's going to give us right. The rounding is, we're going to lose something maybe small, but when we do this conditioning, it could be that already the LP gets rid of a lot of its. It already plays with the objective value, and now we're losing very little relative to this new solution. But this new solution is very far from the original solution. And I think in the interest of time, I won't explain exactly, but you can write it out very simply, even for more complicated LP hierarchies, instances where you do one conditioning step and the LP just throws away half of its objective function value. And then, you still get 2, but we had 2 with a much simpler LP. There's no need to do this whole hierarchy business. Okay, so where does the SDP-ness or the PSD-ness come in, it comes in preventing the relaxation from throwing away the value of the objective function. And it's because we have these second moment matrices that are PSD. If you sort of you use that in the right way, and then in some sense, okay, so it depends. In fact, before our work, there was a work of it was Anna Carlin, Claire Mathieu, and Tach Nguyen. They showed something similar for the Lassalle SDP hierarchy. Like I said, sometimes you have these very powerful tools, and they work for very mysterious reasons, and then it in some sense, it's not as illuminating because you're sort of throwing such a heavy hammer at it, and then it works, but in fact it's hiding something much simpler. So they had some big decomposition lemma, which said that solutions to the Lassalle hierarchy decompose in some nice way, which sort of into something that's 0, 1 over the set you're really interested in. But it's a lot more than we really need. And one of my goals is to really understand sort of one tool where we can really say, okay, these are the positive results and these are the negative results, and they more or less match up. So what I'd like to do is talk for maybe 15 minutes or so about how we use the LS plus hierarchy and get this 1 plus epsilon. I can tell you the exact dependence, but then I also don't want everyone to fall asleep. So it seems like if you want to take a break, this might be a good time. So, is it okay?
So we started at 10, right?
Yeah.
So maybe how long would you need still?
Maybe 15 minutes.
Oh, okay. So do you want a break? We could also just go on, I guess. We could also just go on.
An up and down vote. No one wants to filibuster. Okay, fine. So, okay. So we want to. Okay, so we're still going to do the same algorithm. We're going to. Okay, up there. We're going to take this set, which is all the items which are at least epsilon times the optimum of. Now it's going to be. Now it's going to be optimum of the SDP at level K. And we're going to use the fact that in some sense we're not going to lose much. So the whole sort of analysis that I tried to explain before, where you pick one item at a time and then at the end you don't lose too much, it's going to also use the fact that the value of the objective function doesn't change too much as we do these conditioning steps. Okay, and we're going to do this, we need to understand what exactly I mean by the fact that you can condition and not lose in the value of the objective function. It's not actually true for every index. It's going to be true on average for some weighted average. And so let me just define this weighted average. So if we have some fractional solution to anything, any xi's that are between 0 and 1, xi, I'm going to define a distribution and I think this is really, if you take anything away from this talk, I think it would be this. I think it's my most important contribution here, and that's the use of the Greek letter Sampi, which is it's very obscure, but I'm really I'm trying to get it into the mainstream. So, sort of my two goals in life are to get people and algorithms to use hierarchies, and to get people in general to use the letter Sampi.
How do you write it in tech? Is it possible?
It's a little bit tricky.
There was some imaginary paper called on a sentences asserting their own analytics ability. So this might be one.
Right. No, there's. I've used it successfully, so I know the trick to get it to compile correctly. You can email me and I'll send you the code. Okay. So, right. So the distribution is just defined as follows. The probability over this distribution of choosing index I from 1 to n is just going to be its share of the contribution to the objective function. So if the objective function is summation somewhere over xi ri, then it's going to be xi ri over the value of the total value of the objective function. And it turns out, if you sample the index I according to this Sampi distribution, then you use that I to condition and get this x1 solution, then your objective function value doesn't decrease. Okay, so where's my claim? Right, so the claim is that if x is some solution to level k of LS plus, k is anything greater than 0, so you can do at least one round of conditioning, then the expectation over I sampled according to this weighted average of summation xj 1 rj, where this is this is according to index I in basically the ith column in my is what gives you this specific x1. Then this is greater than or equal to the original objective function value. So there's always some index I which you can choose. In fact, we know how to sample it so that on average you don't lose. There's always at least one that you can choose and you won't lose anything. So ideally what we would like to say is we're really going to do this, right? We're going to choose the index that we can condition on and get some LP value, some objective function value which doesn't decrease. And then at the end, when we do the rounding, we're going to lose relative to something that's at least the original SDP opt, and we're only going to lose this small up there, this small reward. So everything will be okay. the problem is that this is some weighted average. This is not for all I. This is for certain i's. So what happens is that in some cases, it might be that, say, the items that we really want to, or the indices that we really want to condition on, are not the indices in S epsilon up there, but they're in the other set. What we do know is that on average, this has to go up. So what do we have? Either it goes up on or it doesn't decrease too much on average for the heavy set, for S epsilon, and then we're absolutely fine. Or alternatively, it does decrease for the set of heavy items. But we know that on average it can't decrease. So it must compensate somewhere. And it's going to compensate in the light items, in the items that are outside of S epsilon. So now this is very strange. What we're going to do is, okay, so if conditioning on I in S epsilon decreases the objective function by, say, at most 1 minus, and we're going to take, let's say, order epsilon squared, something like that. Then this is, this is fine. We can do this 1 over epsilon times, and we're going to lose something like 1 minus epsilon, which we're okay with. So then we can condition on I and get x equal 1, and we're fine. Oh, it just erased whatever. Oh no, this is okay. On the other hand, otherwise, if there's no such good I in S epsilon, that means that on average, we have a reasonably large decrease in the objective function for S epsilon, and then in the remaining items, we have a reasonably large increase. So otherwise, we have some increase in when conditioning on I not in this set, but at least according to this weighted average. And I think I won't get into the actual math of how much this decreases and how much this increases. Just note that it increases by some function of epsilon. So it's 1 plus, it will grow by a factor of at least 1 plus some factor of epsilon. And we're going to actually choose some I which makes the objective function value grow. Now this is very strange because you would think, we're already done, right? I mean, what's wrong with that? If the objective function goes up, then rounding relative to it in a minimization problem, it doesn't hurt us. So you think, okay, we're fine. But the problem is that somehow we have to say, well, at some point it should stop. I mean, otherwise you would just say, okay, we have possibly almost n items in the complement set. So you don't want to, you would like the argument to stop at some point and say, okay, we can't do this anymore. There has to be some good item here. And the idea is just, if you look at what happens to the value of the objective function, right? So you have, so here you have opt, and somewhere here you have, say, okay, this is opt of SDP, okay? And now suppose we're always in this bad case, where we can choose some item which makes the objective function go up, right? So in the bad case, what's going to happen? We're going to have, say this is opt k, this will be opt k minus 1, opt k minus 2, and so on. At some point, if this keeps increasing by some constant factor, say 1 plus, doesn't matter what it is, epsilon cubed or something, it's 1 plus epsilon cubed, but it's not important. At some point, there's going to be this gap which is, since we're always increasing by a constant factor, at some point the gap is going to be greater than 2. But the gap, even for a much weaker relaxation, is never more than 2. We already showed this. So that would be a contradiction. So there has to be some constant number of rounds that the objective function can go up before we actually contradict some much more basic fact that we know about a much simpler relaxation. And this already captures that relaxation. So this argument would give you a relationship which basically says if you use k rounds, then your integrality gap will go down to, okay, so this says, k rounds, and the integrality gap is at most 1 plus order k to the minus 1/3. I think, I don't want to make any promises because I'm being recorded, but I think the right relationship should be 1 plus order 1 over k. We can get it down to 1 plus order 1 over square root k, right? And it's a very simple, it's a 2-minute explanation. So here we use the fact that the integrality gap is at most 2 in order to prove that the integrality gap is actually at most 1 plus something much smaller. So there's some kind of disconnect here between what we're relying on and what we end up proving. It's certainly not going to be 2, it's going to be in fact something much smaller. So we bridge this gap by sort of bootstrapping this argument. So you just use induction, you say, okay, we have, let's say another k rounds we could use that we're not using, and we proved by induction that for, say, k over 2 rounds, the integrality gap is at most 1 plus order 1 over square root k, and then, that will give us a contradiction much sooner, because we don't have to grow until the gap is 2, we can grow until the gap is 1 plus order 1 over square root k, and then that actually makes sense, right? Now you don't have this disconnect between what you're using and what you're proving, and it's much neater. Still, at some point, I was really convinced that 1 over square root k is the right argument, and then we tried to construct some matching integrality gap, and we painted ourselves into a corner. So I really think that the more logical answer of 1 plus 1 over k should be correct. And it would be nice, because that's what is known, at least from the positive side, for the Lassalle hierarchy, and sort of more generally what I'd like to do is see if we can, bridge this gap that we seem to have in general in approximation algorithms, at least the ones that use hierarchies, where we use these very weak tools to show lower bounds and say, okay, these relatively weak tools like Nova-Schreiber, only, or they have large gaps, or they have large gaps for a few rounds. And then on the other hand, we say, oh, let's take the heaviest hammer, like the Lassalle hierarchy or sum of squares hierarchy, and use that for our algorithms. If we could, like in this case, take something that we knew we had a very heavy hammer for, and sort of move it into the world of simpler relaxations like Nova-Schreiber, we would really understand this whole field much better. And ideally, I would like this to work in both directions. If this is for the positive side, it would be nice if even for the negative side, we could take all these constructions that we have for integrality gaps for Nova-Schreiber or for LS+, and somehow translate them by some nice rounding trick like this, or some other nice rounding trick, to give us gaps for, say, sum of squares, which right now we don't really know how to do very well. Okay, and that's all. Thank you.
Okay, thank you. So, questions?
I have a question. So, if you try to do a similar business for feasibility kind of questions for a knapsack, then you really seem to be getting stuck. Am I correct? Yeah.
For which problems?
Because I remember many years ago we looked at something like, imagine you have, instead of an inequality knapsack, you have a
Exactly.
equality in the knapsack, and then you put, I don't know, you put like so it's 1/2 on the right hand side. So then it is an infeasible problem.
Right.
So now you want to use some kind of hierarchy to prove that it is infeasible, and we were able to show that you should go as far as like 1/2 over the size of the problem in that lifting. So it's something quite different from the nice behavior we have here.
Was it a linear program?
No, and SDP.
SDP? So you're saying, so you're not capturing like some very simple branch and bound trick, right?
Just it's about the size of moment matrices you have to go to, and it is huge. So somehow there seems to be some kind of.
So is there an approximation gap there, or it's just a feasibility?
If you just have a feasibility question, is it sort of related to?
So again, so what do you have? You have something completely in.
Something like.
Yeah.
And your XI 0, right? So you want to produce a certificate using SDP. And also that certificate, so whenever you can choose a lesser hierarchy. Actually, I think we did even before the work of lesser, so maybe it's 15 years ago.
But it doesn't seem like you could really have half, right? Because if you...
No, it is an infeasible problem. You want,
I understand. No, but it can't really be this, right? If it was really this, then just one round of LS would... Yeah, maybe 1.5 or something.
Oh yeah, maybe it is like, so this is from 1 to n, I guess.
N over 2. Yeah, and then n is odd, then I can see that.
There's an intuitive explanation for that, which is for the integer programmers here, when you got to level k of the Over-Schreiber hierarchy and the Schreiber-Adams one, you get all disjunctive cuts that can be derived by disjunctions on k variables. And to eliminate something like that and prove that's infeasible, you need a bigger disjunction. You need a disjunction, or a different kind of disjunction, what's called a split disjunction.
Yeah, I mean it's very consistent with what we have. I mean we can only get something, even in what we hope for. We would like to get a relationship which is basically, a gap of. In this case, to disprove this, you want a gap of roughly 1 plus order 1 over n, and so even if we got this down to 1 over k, you would need k to be order n to witness this. So it makes sense. I think that's the right dependency. And if you say, even for SDP, for what did you use?
I think what?
Which Which proof system did you use?
Hierarchy. As I said, it was before Lasserre, but I
Right.
guess, yeah, well, I should look at that all
Okay, yeah.
to tell you exactly.
Okay. I think definitely for Lovász, for LS plus, this is the limit of what you can do. This.
I mean, I think basically what we did, we wrote down this moment of metathesis, and then
Yeah.
sort of you want to get them not positive, semi-definite,
Yeah.
to see
That's,
that
that's
there is
basically, yeah,
yeah,
that's,
so
that's
that's
basically,
what we did.
that's sum of squares, basically.
Yeah.
Yeah.
and the answer was that you have to go to the size approximately n over 2 to get a certificate.
Right. Good. So that might be a matching lower bound for this other, the earlier result. That
Yeah,
was
good.
used. Yeah, sum of squares. Good.
Other questions? Well, since I was always thinking of his problem, I might have missed some other.
Yeah.
I might have missed some parts of your talk. So, but maybe so. Excuse me if you have told it. Probably you have told it.
Oh,
So, the essence then at the end was that the Lasserre hierarchy works very well for Knapsack, right?
Mhm.
But Lovász-Schreiber doesn't, or am I wrong?
well, what we already knew from this earlier paper is that you seem to need to use SDPs to
Yes.
capture
So
this problem.
LS plus works?
Yeah.
Okay,
Yeah.
I see.
Yeah.
And is there an easy way to explain, probably you did it, where the semi-definiteness comes in?
Yes. So the point is to sort of imitate this combinatorial algorithm. What we need to do is sort of take one item at a time and condition on setting it to 1. And you can use LS plus or Lasserre or whatever you have. And if you can do that and you don't lose anything in the value of the objective function, then the whole analysis of the combinatorial algorithm goes through. But what happens for linear programs, even more powerful ones like Shirali-Adams, is that somehow linear programming doesn't really capture on its own this notion that you need to be honest about the function of the objective value. It allows you to take some fractional value, condition once, and throw out, say, half of the value of the objective function. And then you're going to you'll round this new solution. You might round it very well, but you're rounding relative to something else. You're not rounding relative to the original optimum. So what SDPs, even just a second moment matrix, if it's PSD, allows you to do is say, there's some weighted average of indices where if you sample correctly, you can sample without any decrease in the objective function value at all.
Okay, and there you need really a positive semi-definite.
That's right.
Can you not do Shirali-Adams and then impose the semi-definiteness as well?
If you just have one global, basically you have, the question is semi-definiteness on what? If it's just on the single tag, maybe 0.5 or something, but it won't go down to 1 plus epsilon. Yeah,
You
it will-
try.
Hmm?
You try.
I didn't think about it too much, but I thought about it a little bit, but it seems it shouldn't be hard to construct. Just take a simple integrality gap for some SDP. I'm guessing it should go through, or maybe you tweak the constants a little bit and it will go through when you put Shirali-Adams on top of it, because Shirali-Adams, it just doesn't capture this notion that you're not allowed to throw away something in the value of the objective function.
I've got a kind of philosophical question. I don't know how to say it very well, but would you say that if you can approximate the problem well, that there should exist a natural relaxation of a polynomial size that has the same error? And vice versa. So if somebody proves that an alpha relaxation has a certain ratio, certain integrality gap, that there should exist an approximation algorithm that gives you the same. Do you know what I mean? So that, but it all depends on what you mean by natural.
Well, it also depends on what you mean by approximation algorithm.
Yeah.
Because if you have a natural relaxation with a small integrality gap, if you only want the value, then you have an approximation algorithm.
Oh, yes,
Question
what's the
is if you-
solution? If you actually want the
If you have
solution.
yeah. I mean, in general, that's what we see. That's what happens. But if there's some cosmic reason why it always happens, and I don't know. I mean, what I like to do is try to make these sort of arguments as universal as possible. But yeah, it's a good question. And the first direction. It's a little mysterious. I mean, it seems like if you have a lot of good combinatorial arguments go through very nicely with sort of some of these convex optimization tools. Some of them, it just seems like we can't really capture, like some naive things, like Gaussian elimination. Like, maybe from an approximation point of view, it's not bad, but from an exact point of view, it just doesn't seem like we can capture that. I mean, there are integrality gaps, which maybe some people have, but at least from an exact computation point of view, you can't do, in some cases, what Gaussian elimination can do. It's surprising. But maybe I don't know. Maybe that's a very specific sort of sub-area, tricks in linear algebra that just don't go through here because you need to see a lot of variables at once in order to do it. But maybe in most cases, I think graph algorithms, should translate nicely.
So, what do you mean Gaussian? I mean, Gaussian elimination should be already at the first round of Lassé relaxation.
No, it's actually. Hmm?
You have to say it's over F2, right?
Over F2.
Oh, you mean over F2?
Yeah.
I see.
Yeah.
Okay. Yeah. Then it gets very combinatorial. Yes.
Yeah, and
Okay.
that's known not to be captured by the cell.
At which level? I mean, at some level it must be captured, right? If you have n rounds.
N rounds, yeah.
At the very last step.
Yeah, linear number. Not surprising.
Okay, other questions? No, if not, we thank the speaker.